Hello, everyone, and welcome to the Slightly Scientific Podcast with me, Oliver, and sitting next to me virtually, as always, is Finley. Now, sadly, Stacey could not join us. She's feeling a little bit ill, so hopefully she gets better. Anyway, we hope you enjoy. Today, we are going to be interviewing Rob O'Connor, who is a geologist and a geophysicist. Now, before we interviewed him, we honestly had no idea what a geologist even was or did.
Wait, what do I say? How do I wrap up a geologist in one sentence?
Geologist in one sentence. Study the earth is one thing.
I suppose it's also geophysics in a way.
Yeah, I mean, like, what they do is they study the earth, the insides of the earth, to see where pockets of minerals, oil, etc. is, so companies can dig it up. I think that is.
I searched up for geology in one sentence, and it came up with examples of geology in a sentence. The geology of New Mexico is fascinating.
Is that like a dictionary where it gives you an example sentence? It is. Oh, that is amazing. Anyway, before we go on to that, we've got something very important to do. We need to announce the fact of the month. Now, normally Stacey would be doing this and all of this and everything. But sadly, again, she's not here. So, Finny, you're gonna have to take over.
Wait, I found the good definition. A geologist is a person who studies the history of the earth through rock and rock formations.
That is lovely. Except, Finny, we're on to the next bit. You need to do the fact of the month.
What's the fact of the month?
I couldn't.
The Eiffel Tower expands up to 15 centimeters during the summer because of thermal expansion.
Because of thermal expansion. But
because
what is
you know how
expansion?
it gets hotter, it goes like.
Oh, is that like train tracks and like bridges? Now, if you would like your scientific fact featured on next month's podcast, make sure to tweet us at The Slightly Sci or DM us on Instagram at The Slightly Scientific Podcast. Now, on to the interview. Finny, you're meant to say on to the interview.
Now, on to the interview. What does it mean to be a geologist? What does a geologist do to start?
Well, a geologist, there's a lot of specialties within geology, but fundamentally it's a study of how the earth works, how the earth moves, how the rock record is built in the earth. So I don't know what you know about geology, but the earth is not static. It's made of these giant plates that sit on sort of a slightly fluid surface. And new earth is always being created in the middle of the oceans, along mid-ocean ridges. There's volcanic rock that comes out along these long ridges, and it's always being consumed under what they call subduction zones. A classic subduction zone would be the northwest of the United States, under, say, the state of Oregon and Washington, where oceanic crust is going down underneath the continent of North America. And when it melts, it creates volcanoes. So there's a whole series of volcanoes. The one that's most recently exploded in the Northwest is Mount St. Helens. About 25 years ago, it was a very large eruption.
So are these are these like tectonic plates then?
Yes, indeed.
So that's the destructive boundary when they create volcanoes.
So the subduction zone is the destructive boundary. The mid-ocean ridge is the constructive boundary where new crust is created. And so geology, a lot of geology, a lot of what I did was oil and gas geology, which is the study of basins and how sedimentary rock, which is rock that's eroded off of continents and mountain ranges, gets placed into these basins and the layers that it forms and how different layers can create oil and gas and trap oil and gas in subsurface structures that can then be drilled, captured, and produced so that for cars, for natural gas, for stoves or power plants, that sort of thing.
Well, how is the oil and gas produced from?
It's a long story. So oil and gas is basically, you see those cartoon ads where dinosaurs get buried and made, and gradually get heated up under layers and create oil. It isn't dinosaurs. It's much more boring. It's algae, or microscopic animals. And typically when they gather in very oxygen poor water, stinky. Have you ever seen a stinky lake that you've got not quite wanted to swim in? Someplace like that, because the oxygen, well, it oxygenates the organic material and it doesn't get preserved. So it's in these stinky areas where it gets preserved and it gets buried, and just with the process of pressure and temperature, it's it heats up and it generates oil. Now oil is buoyant, and all these rocks are porous. So if you ever spilled your drink on the beach, it vanishes instantly because that sand, soon it was one day to be sandstone, is so porous. And so it gradually, just through buoyancy, works its way up until it finds a porous rock with a non-porous rock above it, and that's where it gets trapped for, ultimately anywhere from 1 million to 500 million years. And it's produced by drilling into it, which is a whole science and engineering industry in itself, because a lot of the wells that I've drilled have been offshore in anywhere from 100 meters to 2,000 meters of water before you even get to the seabed. Oh, wow. And then the wells themselves can be 1,000 feet to 5 miles deep.
So these are really deep. That's like all the way underneath the ground, these the oil.
Yeah, it's underneath the ground, and typically it's underground and it's under high pressure because there's so much weight of rock above it. And so it flows into these wells when you drill them. They have to be very careful to put steel in the well and cement it into the rock quite carefully so there's no leakage, because you need it to be a controlled, sealed system. Otherwise, you get these horrible oil spills, as you've probably seen in different parts around the world.
Perfect. Why did you choose to become a geologist?
Well, it was just because it was fun. It's sort of a silly reason, but I grew up in California in a place called Palo Alto. And when I finished high school, I didn't know what I wanted to do. And I went to what was called a community college, which was great because it was free and it was a 2-year college. Okay. And I studied chemistry and biology, and which I quite enjoyed. But I didn't know exactly what I wanted to do with it. And then one day I took a geology class, and we got to go outside and look at rocks and measure rocks and examine them and talk about how they were created, whether they were volcanic or sedimentary rocks, or even what they call metamorphic rocks, which are rocks that have been well beneath the surface and squeezed and changed or metamorphosed into something different. And then later eroded, the earth was eroded and they're exposed to the surface. So it was like doing chemistry or biology or something, but the classroom was outside. And I found that quite fun, because I always really enjoyed the outdoors and the mountains. And that's what perked my interest. And then I went to the University of California at Davis, north of where I'd grown up, which is near Sacramento, California. And I studied geology as an undergraduate and did more field work and didn't find a job when I got out. Well, actually I did. I started work with the US Geological Survey. Okay. And there I learned about geophysics, which was using physics methods to try and image the subsurface. So rather than just having a little borehole and a core of rock that's 6 inches across to try and understand an area, you could try and image huge areas in either these 2D lines or in 3D cubes.
How would you image those areas?
So it's by putting energy into the earth. So onshore, you would use these big machines to vibrate the earth, or you'd use dynamite, and you'll send a sound wave into the subsurface. And where the earth is layered in multiple layers, this sound wave continues to reflect back up to the surface, and you record that with these very sensitive vibration sensors called geophones, or hydrophones if you're in the water. And by doing it doing it over and over through redundancy, you can sort of sum all these signals and they get clearer. So there's a lot of geophysics is for geology. There's lots of different kinds of geophysics. There's electrical methods, but what I did was seismic. And it's a lot of signal processing, a lot of use of what's called the wave equation to try and understand how this energy moved through the earth and was reflected back, and how to reject or filter out noise so that you could see get an actual image or a cross section of the earth that goes down, really as deep as 20, 30 miles in places, or 40, 50 kilometers. But for oil and gas, the interest level never gets much below 10 kilometers because it just gets too hot, and it also is too expensive to go that deep.
How accurate were these pictures that how would you, because it's waves of it and you do it loads of times, I understand, but what would be the resolution? Would it be easy to make out what's what?
So the resolution is, let me think about this. So we think of the revolution in hertz, so in vibrations per second, but the resolution is very high in shallow parts of the earth. And because the earth absorbs the high frequencies of the sound, preferably the low frequency, you only see the much longer wavelength waves. So it gets much less as you go deep. So let's say, in the upper 100 feet, where I did work in New Zealand, where we're looking at the upper 500 feet, looking at earthquake faults and trying to map active faulting and predict seismicity in areas. There we could see, we could see features as small as sort of 10 feet or 3 or 4 meters. When you get down to 6 or 7 kilometers, you can see vertically only about 150 meters. So it gets much less.
Yeah.
Now, laterally, it's more precise because you can see spatially very clearly. But to give you an answer, we don't often know what's down there. We know we can see reflectivity. We know that's a surface in the subsurface, but we don't always know what it is. Probably historically, oil and gas wells, I'd say 1 in 5 have been successful over the history of oil and gas drilling. So there's a high chance that you don't know what's down there, which makes it quite interesting and fun.
Yeah.
And it's quite a puzzle because you're trying to pull together information from this image together with older wells, possibly with rocks that you've seen in outcrop on the onshore, and you can map them on the seismic down to where you are so you can have a guess at what's actually there.
Yeah.
And there's a whole science of looking at the types of surfaces and images you see to try and predict what kind of rock you might find, whether it would be a sandstone, whether it would be a mudstone, that sort of thing, whether it would be a source rock.
I see.
So there's a lot of guesswork.
Yeah.
And putting together very little information to assemble the clues and figure out what's down there.
That sounds like fun. That's like a bit like detective work almost.
How long does it take to set up all this equipment?
So it takes a while. So, if you want to, it's easier offshore because you tow streamers and you tow your sources, which are actually air guns, which air guns are a whole nother issue because a lot of people are quite concerned about the impact of the loud noises they make on whales and dolphins and marine mammals. And so on any seismic vessel, you have to have many marine mammal observers. Typically, there's a lot of regulations and a lot of permitting to do to make sure that you're careful. You have to start up carefully. You have to be watching for mammals and stop if you see them. But that's how the energy is placed into the earth. And then the boat moves along and the energy bounces off of the subsurface and it's recorded on these what they call streamers, vibration sensors or hydrophones that are probably 10 to 12 kilometers towed behind the boat.
Okay.
So that you get a whole range of angles off these different things in the subsurface. Typically, from the time you start planning a survey offshore to the time you get the data back and fully computer processed to get a full image, it can be 1 to 3 years, depending on the size and complexity of the project. So it's not fast.
Wow.
And similarly onshore, where you have people that go out and which I've done, you push these geophones into the earth on a spike so that they can measure, and you'll put out large grids of them and then put energy either through dynamite or these big vibration machines into the earth. So it's a big job and it's often quite expensive.
Oh, and these streamers you were talking about, how big are they?
They're typically about between 2 to 4 inches across. They're very thick plastic and they're filled with oil, so that they're all in a fluid that's similar buoyancy to whatever fluid you're in, which is typically seawater.
Seawater. Okay.
So that they'll stay at one depth, and then those plastic tubes are filled with all these vibration sensors and electronics.
How else do geologists study the Earth, and what other tools do they use?
So a lot of geologists, a lot of geology can be observation. So people going out and making maps of the rocks they can see, and you can typically see the rocks very well along a coastline, or in a desert, or in the mountains. It's often harder to see the rocks in a forest or a very green area like much of the UK because it's covered with grass or soil or trees. But there's a lot of observation and mapping. There is, people when, you'll always see geologists where there's a new road cut or a trench that's being done because suddenly there's geology exposed and they'll want to go see it.
Yeah.
I did one project, one of my very first things when I worked for the US Geological Survey was up in the Aleutian Islands in Alaska. And there we drilled samples all along the coastline, very small samples, but we measured their orientation because rocks, very fine-grained rocks, there's always a small amount of magnetite in them, and they line up with the current Earth's field. And so there's a whole study called paleomagnetics, where you can understand how different the declination and inclination is from a rock that you've taken in a sample from the current Earth's magnetic field. And you can predict whether that piece of rock has moved north or south or east or west or rotated since it was deposited. So that's quite an interesting science, really.
That's very interesting because you can always look back in time to see how this rock was aligned with the Earth.
Yeah, and I guess the fundamental principle of geology is that rocks are in layers in sedimentary basins, and the one thing is that the shallower the layer, the younger the rock. So they always get younger because a basin fills from the bottom up.
Yeah.
And the only thing you have to be aware of is when there's a lot of folding, they can be upside down. And you have to undo the structural geology or sort of recreate what it was when it was first put down. So if you look at the Alps and pictures of the Alps, you see the rocks are all curvy. And so those are original oceanic basins that have been uplifted, well, first buried, but then uplifted and folded quite severely. And so it's there's a whole study called structural geology to try and understand and unwind that to try and predict what that basin was long ago.
Oh, and
So the deeper you look, the farther in time you go, further back in time you go.
Yes. Yeah.
and
Yeah.
and
And then there's people who study fossils and try to understand, they can then date some of these rocks because they know when certain animals lived. So say in what's called the Cambrian, or 500 million years ago, there's lots of these small animals called trilobites. And you can, when you go back in time, you find beds full of those, and you know sort of that you're in some very, very old rock. And, but there's people who have studied it called paleontologists, and they've sort of worked this out all around the world. But there's still guesswork. It's still plus or minus a million years or 10 million years a lot of the times when they're trying to date these things.
What would you say is the importance of a geologist? As in, what do we use in the modern day that geology has helped create?
Well, so I'll start, there's a lot of things, but let's start with energy.
Yeah.
So now it's changing. So I'd say that the job that I've had for all these years of looking for oil and gas is one that's going away. And hopefully it does go away, because we're putting too much CO2 into the atmosphere, and we're damaging the planet horribly. But anytime you throw a light switch, anytime you turn on your stove, you get into a car, you get into a bus or a train, probably 80%, 90% of that power is still generated by oil or gas. Oil and petrol, is actually, the problem is that we use too much of it.
Yeah.
It's not that petrol isn't the problem. It's that there's now 6 billion people using it every day, and we're putting, too much of anything can be bad. But, petrol in a gas, in the tank of your car is a great energy storage. It'll take you 300 or 400 miles without refilling, and it's completely mobile, and it's transformed people's ability to move around, and it's quite freeing. If you have a car, at 13 you don't have one yet, but there's quite an element of freedom in being able to get in your car and go anywhere, with or without a train timetable or a bus timetable. But so that's one. I guess the other is minerals. So there's I've never worked in the mining industry, but most mineral samples, whether it's iron, whether it's lithium for batteries, which is quite important right now.
Oh yeah.
Whether it's uranium, those are all things that geologists have worked out the types of rocks that they're found in and the environments, and gone out and looked for them and found mines. Diamonds come in these very peculiar things called kimberlite pipes that were once 40 kilometers below the surface, in a very interesting type of rock. So I'd say, anything that's a metal or a stone, geologists also look for gravel deposits. I mean, you might say that's pretty common, but where can you mine a lot of gravel if you want to build a concrete building or a concrete city, like some of the cities in China? So sand, clean quartz sand is used for all our glass. So sand deposits. So it's quite diverse and fun. But the last of the really big industry that employed a lot of geologists is oil and gas, and I think that's one that's on the wane now.
Yeah, but you talked about lithium, and of course, for the reusable energy, with you need batteries to store the energy in. So I feel lithium is a very valuable kind of thing for our energy storage.
Yeah, it's hugely valuable, and it's it's very important to find lithium deposits, and because it's like many things, not a limitless resource. It's also going to prove to be very important, I think, to try and recapture lithium when batteries reach the end of their life, and not just throw them in the tip, but to capture that lithium and reuse it and make sure that we're not wasteful when we use it. But yeah, so there's, it's one of the things that's quite important right now. There's a few other specialized minerals that are used in, say, mobile phone technology.
Oh,
that I can't think of what they are right now, that are quite rare. But any mineral that's mined from the earth was probably found by a geologist.
I think that's actually all the questions. That's everything done. Thank you so much.
Oh, you're very welcome. And I think, I think if I were interested in the energy industry now, I'd probably be studying how to, engineer windmills and engineer solar and things. But that wasn't where I was 30 years ago when I studied geology and geophysics. But I'm very pleased to be able to talk to you. I think this is quite fun, and I've enjoyed it. So thank you.
Thank you. Yeah,
Thank you.
really nice to talk to you. We've learned so much during this. Before I've never really thought about where we get all these metals from, how people have discovered and where they are. But it's really interesting to see the process to try and uncover these metals and to find them. So thank you so much for talking to us. This has been amazing. Thank you.
Oh, you're welcome. Thank you, Oliver. Thank you, Finley. It's been a pleasure to chat with you.
Thank you so much.
Okay.
So thank you so much, Rob O'Connor, for letting us interview you. It was really fascinating listening about what geologists do, how they study the earth, and we really enjoyed it. Thank you so much. And thank you guys for listening. We will be back next month with another podcast. Stay tuned. And make sure to follow us on Instagram, Twitter, Facebook, and wherever you get your podcast from.